Yeah, then welcome everyone. So I think most of you might know me by now. I'm a climate researcher currently working at the SMHI Bolin Center, and I'm also doing long-term climate studies at the Department of Geology at Stockholm University, and I'm one of the research area leaders at the Bolin Center. So today I will give you a brief update about what's going on with the Gulf Stream system. So we might have seen that there was some report on SVT that the Gulf Stream system is rapidly slowing down. And that's partly also things I work on, and also SMHI looks into these things. So that's really an important research topic. And so today I give a brief overview about the most recent papers and relate them a bit to what we know from the last IPCC report. So that's basically what you find in the summary for policymakers. So if you look for the AMOC, which is basically the abbreviation of Atlantic Meridional Overturning Circulation. So that's basically when scientists talk about the Gulf Stream system, we actually mean the AMOC. And if you search for that keyword, you find it 3 times in the summary for policymaker. And I was really pleased to see that it's very accurate what they write there, and I sign that 100%. So it really shows that these reports are very well done. So that is from 2019. So maybe the science which is included in that goes until 2018. And there you see that there's a medium confidence that the Gulf Stream has, or the AMOC has already weakened. And also there's quite some agreement that the Gulf Stream or the AMOC will slow down under future warming. So that's quite clear. And so basically in the second part, you see here that the AMOC is projected to weaken, and that's very likely. So this is quite, we are quite sure about that. And there are hardly any models which don't really show a slowdown for the future.
Freddie, you turned off your microphone.
Yeah, okay. It seems you can hear me now? Okay, sorry. So based on the IPCC report, it's very likely that the AMOC will slow down. And the news is also based on climate models. The stronger the warming, the more the system will slow down. That's very clear. So the question is not if the AMOC will slow down, but rather how fast and how rapidly. And there were some new studies now which shed a bit more light on the long-term perspective. And one study was in 2018 that was from a bunch of very well-known geologists. They reconstruct basically the overturning system from different proxies, so from indirect evidence from the ocean sediments. And what they already wrote at that time was that the overturning is very weak in the last 150 years compared to the last 1,500 years. And a new study, which was now in the news, is basically from Cesar et al. And that confirms that results by bringing even more data, which shows the same. So it's basically, these two papers are connected, and also the author of Tornelli is basically included in that. And the difficulty, if we want to look into long-term changes of the overturning circulation, is that we cannot see it. So even today, we have measurements starting in 2004, but before we don't really see anything which is going on in the deeper ocean. So we have to reconstruct that, have indirect definitions and reconstructions, and then interpret what's going on. And the most recent result is that there's a warming hole in the North Atlantic. Ramsdorff 2015 published that, and this warming hole can be interpreted as something we see at the surface of what is going on in the deeper ocean. And also these reconstructions, which have been now done based on marine and terrestrial data, they make use of this definition. And by doing so, they can show that there is a slowdown. So the definition or the characterization of the Atlantic meridional overturning circulation might be well known to most of you. So when we talk about the Gulf Stream, typically that's the exact definition of the Gulf Stream is only the small part around Florida and the US coast. And then the westerly winds transport the warm water towards Europe, and that's the North Atlantic current or the North Atlantic drift. So if we talk about a Gulf Stream weakening, we actually mean the North Atlantic current. And that's basically the concern, that if that is slowing down, we will have drastic impacts for Europe, for the Arctic, and also global impacts. And a movie Day After Tomorrow is an extreme version of what in the movie happens. But that's unrealistic, most of it. But we know from the past that the impacts are really drastic on Europe. So that's not really something we should do. And what is important to understand this overturning system is that it's in the north, in the Arctic and subarctic region, driven by cold water and salty water. And that increases the density of ocean water to sink to the deep. And only if water can sink to the deep and go southward in the deep ocean, the warm water can go north in the surface ocean. So this is connected. As soon as the deep water formation stops, also the overturning stops. And as you can imagine, if we now warm the atmosphere, we also warm the surface ocean. So the water gets less dense, and it's not as easy to sink into deep. And what comes on top is that the warming leads to more precipitation at higher latitudes and also more melting from Greenland ice. And that also decreases the density. So the combination of more fresh water and warming will slow down the overturning system. And what these new studies indicate is that this slowdown is already on the way since almost 200 years. So we actually only see the most recent slowdown and might have started much earlier. And based on theory, we know that this overturning system can be unstable and can also stop. So we know that based on theory, but we can also observe that in proxy data in the past. So it is possible that this system can be very weak, or it can completely stop. And the question is, of course, when does that happen? And that's a huge uncertainty. And that's why we need to be careful when we do rapid global warming. And I mentioned that if we look on longer timescales, we have indirect information. So basically, we need to first define what we understand as overturning circulation in terms of insufficient data. And that's mainly based on a definition from Rahmstorf 2015, which was then here, for example, used from Kaiser et al. 2018. And this is the observation you see in basically all data sets if you look into them. There's a cooling here on the left side. That's the warming hole, and that's very strong in the observations. And you see the warming south of it. And this is a fingerprint of the overturning circulation slowing down. You see that in the observations, and you also see it in climate model simulations. So if you create now a time series of this blue area, the warming hole, and the warm area, then these time series diverge over time. And that's basically the same as saying that the overturning system slows down. In the left, you see an example from climate model simulation that shows a slowdown. On the right, you see the same definition applied with real observations. So they clearly show that there's around 15% slowdown if you use that definition. And that definition can now be also used if you use geological data. And you can also confirm with a climate model simulation. This is one example here. So you have a red line and a blue line, and the time goes from 1850 to 2100. And the red line is the overturning circulation in the real ocean model. And the blue line is the overturning circulation using this definition of that index based on the warming hole. And as you can see, they are identical. So you can use this fingerprint in the surface ocean to know what's going on in the deeper ocean. And here in that example, you can see that there's a drastic slowdown starting basically now, and that continues way into the future. And basically all climate model simulations show a slowdown, but they don't agree on how much and how fast. So this is very important to understand this kind of definition. And now I come back to these two papers because they use this kind of definition to show that there's a slowdown. And I first go to the Tornelli paper from 2018. On the left, you see again this concept from the modern climate, the warming hole and the, basically the dipole. And in the upper part, you see the red time series. So that's the reconstructed temperature evolution since 400 BP before Christ until today. So there you see the warming. And in the lower figure, you see the time series, the blue one, which shows the cooling. And there you see that starting around 1800, you have a strong warming or a strong cooling, which represent this fingerprint of AMOC. So if you now combine these two time series, you get the final result. And that's shown here in the top figure. That's the reconstructed AMOC. So here you see that it's a really drastic slowdown, which basically starts around 1850. That's the end of the Ice Age. So half of that slowdown is maybe until 1950, and the other half is most recent. And I think this is quite a strong evidence that there is a slowdown. If it's really 15%, like the author says, with uncertainty, but I think it's quite clear that it's slowing down. And this study was then later confirmed by Kaiser et al. 2021 by having more data which shows the same situation. In the middle, you see a reconstruction of temperature in red and salinity, so how salty the ocean water is. And there you see this abrupt slowdown also in the most recent period, which basically confirms that the temperature reconstruction, which shows this slowdown, is consistent with the changes also in the salinity. And I think this is good to have this multiple evidence that you not only look at temperature, but have also independent results which are consistent. And also very important time series is the lower one. So it's a bit cryptic. I also had to look into it, what it is actually, but it's basically sorted silt. So at the ocean bottom, when you have the currents, they transport very fine sediment. And in some areas, the sediment basically accumulates, and how much and how thick the grains are, which sediment there depends on how strong the overturning circulation is. And also that proxy shows clearly that the ocean currents in the deep part slowed down consistent with the temperature change at the surface ocean. So you basically have confirmation from the surface ocean and from the bottom of the ocean that the overturning system slows down. And so the new paper basically shows here a lot of time series, and I will not go into that, but it just shows now in the top, you see that they are now taking from a lot of different locations, and they basically also show this slowdown. And in the right column here, you see even the most recent period from 1900 to 2018 or so. So even though often these marine records are relatively coarse resolution, they still show some of the observed variability. For example, in the most recent period, we had a small recovery of the overturning circulation in the observations. And this is also partly captured by this marine sediment data. So this is really confirmation that these proxies really do a good job. There are still uncertainties about how much slowdown that really represents, but I think it's clear that there is a slowdown. And so basically that's the main conclusion from these studies. And what is really new, even for people who work on this topic, is that this slowdown is so drastic compared to the last 1,500 years. And I think this is really a surprise. We didn't really know that. And a key question is, of course, what is the impact then on the climate? And I will not go too much into details because that would be an own lecture, but I think that is really what concerns us. Because you could argue, okay, slowdown of the overturning circulation leads maybe to cooling in the Atlantic, which is a good thing to have because the warming of the CO2 can be compensated, and it doesn't really work at all. So even though there will be a cooling of the ocean in a very drastic scenario, the climate will be still warming, but you get much more extreme gradients between a cold ocean and a warm atmosphere. And that was also mentioned in the IPCC report that typically leads to more storms, leads to changes in the monsoon system. And we also have evidence that it might lead to more severe heat waves and droughts, for example, in Europe. And that's also something I will look into in a new project the next 3 years. I give you just one example without much context of a simulation I did 12,000 years ago. The last time when we had a drastic slowdown of the overturning circulation, drastic in that climate model was only around 15%. So it was not a collapse at all, but the climate was still at the end of the ice age, so cannot directly compare it with today, but you see already that 15% slowdown back in time had drastic consequences. And what you see here in this figure is just the temperature difference of 12,000 years ago of surface temperatures compared before the slowdown and after the slowdown. So cold temperatures mean cooling after the slowdown, and warm temperatures mean warming. And this pattern is quite consistent with some things we observe currently. The one thing is the warming holes south of Greenland, south of Iceland. That's related to a weakening of deep convection in this area. You see also the slight warming further down in the US coast over the Atlantic. So basically you get again this weak AMOC fingerprint, and the climate model suggests that the response to these ocean changes are warm temperatures over Europe. And from other proxy evidence, we know that there was a collapse in European forests. And that's something which maybe reminds you of 2018. That's exactly what the climate model simulates back in time. So I think this is really an evidence that these things can be connected, but we need to still look into it to prove that. And a key problem, which I think is a bit not, we don't spend enough attention to it, is not, typically we look at temperature, but I think the problem really is if you have a colder ocean in a warming world from CO2, you get a problem with precipitation, because the Atlantic is the major source of water, of precipitation, and that needs to be transported on land. But the warming from CO2 over land basically will require that you have more moisture from the Atlantic. But if you cool the Atlantic, then you get a strong deficit in the available precipitation. And that's something also you see 12,000 years ago. This is changes in precipitation for the different seasons: winter, spring, summer, and autumn. And red and orange and yellow colors means that there's a drastic reduction in precipitation as soon as you really slow down the overturning circulation. And here in this simulation is up to 50%, and that explains why the European forest collapsed. And we have seen 2018 was just 1 year with extreme heat wave and drought, and we see already a collapse of parts of European forests. So it could be connected. It was just one event. We had some more events, But if we are unlucky, it could be linked, and then it looks much more extreme than it's written in most reports. So that's basically where the current research starts. So you see there's new evidence that there's a drastic slowdown in the overturning circulation, and there's evidence that it could be linked to the extreme events we have in Europe. And in the past, we know that this has happened. So there it's actually quite clear. And this is one example from northern Germany. I also don't go into detail, just into the interpretation. This is from a lake sediment core from 11,000 years ago to around 13,000 years ago. That's the end of the Ice Age. And here they reconstruct indirect evidence of changes in humidity, so basically precipitation, and how the vegetation responded to that. So this is typically what geologists do. Sometimes they flip the time axis. So you need actually to go from 13,000 to 11,000 to understand what happened. So in around 13,000, basically you have a normal climate, and then you have a drastic collapse of the overturning circulation. And what this proxy here shows, that it's getting dry. And as soon as the overturning becomes strong again, that's around 11,700, then it gets very wet again. So that's exactly what we also see in climate models. And here you see a reconstruction of how much trees and herbs you have. So herbs is mainly grassland, and trees is basically forest. You see that in the normal climate, you have a lot of forests, and then you have a collapse of the forest. And the forest only comes back after basically the overturning circulation becomes active again. This is really a drastic change, and in most parts of Europe, it meant that there were no forests at all. And in the lower part, you see the green figure. This is also pollen reconstruction for the sediment core from basically Artemisia pollen. That's also something which grows today. So if you have a lot of Artemisia, it typically means two things. First of all, the trees disappeared, and second, it became very dry. So this is clear evidence that drastic change in the overturning circulation can lead to drastic changes in the ecosystems. And if we now look 12,000 years back, we don't see much of that thing. But here you see examples from basically sand or soil layers from different parts in Europe. Here, for example, from the Netherlands and Belgium. So everything which is left from this drastic, abrupt climate change is basically this dark layer. That's maybe how our climate looks in 10,000 years, if you look into the sediments. And this dark layer is an indication of a lot of forest fires, so charcoal, which basically forms this dark color. And that's an indication that most of the trees basically burned and left this dark charcoal layer. So this is clear evidence how this overturning circulation is linked to European forest fires and droughts. You can also go further back to the further east, northern Germany in Poland. You all the time see this layer around 12,000 years. And meanwhile, there's also a publication from Russia, from the Ural, which basically also shows exactly that layer around 12,000 years ago. So we see that this droughts and mega fires, forest fires, basically extended all over Europe into Russia. And I think that's a clear evidence that this AMOC slowdown has drastic consequences. So I stop here. And the conclusion is from that, that nothing good ever came from drastic AMOC slowdown. I just showed you now one example, but there are many more. And I think a problem here is often the communication and also the uncertainties we have as researchers. So I think the day when scientists agree that there's a major AMOC slowdown, it might be the day it is too late. I think this is really a problem. And so the only conclusion, like always, is we should stop the warming now. I think otherwise we will have soon another sediment layer which looks like 12,000 years ago. So I stop here, and if you have any questions, we can start now.